Generalizing the linear model. When the linear model is not flexible enough, we can use the quadratic discriminant function and increase complexity. GA of x conditioning on capital WI, WI0 equals to x transpose times capital WI times x plus WI times x plus WI0, but this approach is big O of d squared, and we again have the bias variance dilemma. The quadratic model, though it is more general, requires much larger training sets and may overfit on small samples. An equivalent way is to preprocess the input by adding higher order terms, also called product terms. For example, with two inputs x1 and x2, we can define new variables z1 equals to x1, z2 equals to x2, z3 equals to x1 squared, z4 equals to x2 squared, z5 equals to x1, x2, and take z equals to z1, z2, z3, z4, z5 to the transpose as the input. The linear function defined in the 5-dimensional z space corresponds to a nonlinear function in the 2-dimensional x space. Instead of defining a nonlinear function, discriminant, or regression in the original space, what we do is to define a suitable nonlinear transformation to a new space where the function can be written in a linear form. We write the discriminant as g of x, which is equals to sigma wj times vij of x, where the sigma summing j starting from 1 to k, and where vij of x are basis functions. Higher order terms are only one set of possible basis functions. Other examples are sine of x1, exponential of minus of x1 minus m to the square divided by c, exponential of minus of the absolute values of x minus m to the square divided by c, the norm value, and also log of x2, and also there are examples such as one function to differentiate whether x1 is greater than c or not. Another example is one function of comparing ax1 plus bx2 is greater than c or not, where m, a, b, c are scalars. M is a d-dimensional vector, and 1 of b returns 1 if b is true and returns 0 otherwise. The idea of writing a nonlinear function as a linear sum of nonlinear basis functions is an old idea and was originally called potential functions. Multilayer perceptrons in Chapter 11 and radial basis functions Chapter 12 have the advantage that the parameters of the basis functions can be fine-tuned to the data during learning. In Chapter 13, we discuss support vector machines that use kernel functions built from such basis functions.